In this video, we'll examine the reaction with lithium aluminum hydride and subsequent treatment with hydronium ion. Carboxylic acids can be reduced by these reducing agents down to primary alcohols. Just like we saw, primary alcohols could be oxidized using strong oxidizing agents to carboxylic acids. So let's consider a specific example. If we have benzoic acid and we first treat with lithium aluminum hydride and then hydronium ion, we can produce the primary alcohol. Let's look at the mechanism below, and to do that we need to draw the structure of lithium aluminum hydride out fully. Lithium aluminum hydride is a good hydride source, meaning it can use one of its hydrogens, specifically the aluminum hydrogen bonding electrons, to do a reaction. Normally, we've seen that hydride act as a nucleophile at a carbonyl, but because carboxylic acids have an even more reactive site, this proton, the first step in this reduction process is removal of the proton. Notice that the proton here is red, not black, because we lose it in the reaction and we regain it later on. So these bonding electrons grab the proton, depositing lone pair electrons onto the oxygen. We see the carboxylate anion form now interacting with the lithium cation. The hydrogen from lithium aluminum hydride paired up with the hydrogen on the carboxylic acid to form hydrogen gas. So this is an irreversible process, and ALH3 is produced as a byproduct. This aluminum is electron deficient. It has an incomplete octet, so it can react with nucleophiles, and this electron-rich oxygen is a nucleophile, so it can attack the aluminum, forming this new oxygen-aluminum complex. So this looks a lot like the lithium aluminum hydride we started with, in that we have a negative aluminum with 4 bonds and it still has some hydrogens attached to it. So it again is a hydride source, and now that hydride source can react at the carbonyl carbon like we normally would have seen with other carbonyls and lithium aluminum hydride. So nucleophilic attack can occur, forming a tetrahedral intermediate where now we have a new carbon-hydrogen connection and a negatively charged oxygen interacting with the lithium cation. This oxygen-bearing group can now serve as a leaving group under these basic conditions, so we can reform the carbonyl and kick off that leaving group. At this point we have an aldehyde, and we've previously seen that aldehydes can also be reduced by lithium aluminum hydride. So a second equivalent of lithium aluminum hydride can supply a hydride to the carbonyl, moving electrons up onto the oxygen and forming the tetrahedral intermediate. With no good leaving groups on this tetrahedral intermediate, the oxygen has only one choice, which is to get protonated, and it can be protonated by hydronium in a subsequent step to produce the primary alcohol, with these 2 hydrogens coming from lithium aluminum hydride and the proton on the oxygen coming from the hydronium in the final proton transfer step.